Okay, so we're going to be looking at what we call risk-loving preferences. So in previous graphs or previous videos, we've looked at risk neutrality, where a decision maker is indifferent to risk. She only cares about the expected value. And we looked at risk aversion, where the decision maker is averse to risk. She does not like risk. Her expected utility is decreasing if risk increases. And now we'll look at the third possibility, risk-loving preferences, where expected utility is increasing if the decision maker is faced with more risk. And we'll use the same example as we've done before. So we're looking at different states of the world. We call them low, normal, and high. Okay, so this is the state of the economy or sales. If you're a firm, if you're in a ski resort, you're running a restaurant, how much snowpack there is, how many tourists there are. You can have two actions. We call them A and B. And we have outcomes associated with the combination of states and actions. Okay, so if there's thinking of the snow cover, you're a restaurant, you choose action A, having say fairly small restaurant, have and the state is low, you have an outcome of 2, and then 4 and 6. These are, of course, just examples, and action B will be associated with other payoffs, 0, 4, and 8. Okay, so crucially, in normal times, or crucially, but for the example, in normal times, they both give the same outcome. But everything is, times are not always normal. It can be either in a low state or in a high state. And here, the different actions imply different outcomes. So action A does better in the low state, whereas action B does better in the high state. Okay, so how should a risk-loving decision maker choose in this case? Well, we have as a benchmark that a risk-neutral decision maker would not care here. If we're thinking at the probabilities are such that the expectation is the same here. So let's assign, or let's put some probabilities here and say that probability is 1/3 that we're in low state, 1/3 that we're in the normal state, and 1/3 that we're in the high state. Okay, so we saw for risk aversion that a risk-averse decision maker puts more weight on low states and less weight on high states. A risk-loving decision maker does the opposite. She puts more weight on the high states. Okay, she doesn't matter so much what happens if things do poorly, but you really like, if things go well, you really want to do well. Okay, so just as with risk aversion, we do this by having a utility function, a von Neumann and Morgenstern utility function, or in this case, as an example, we have y here, the different outcomes. Y squared is an example of such utility function. Okay, so let's look at the expected utility of action A. So U of A. We take the probability of each state times the utility of that state. So the outcome is 2. The utility of that outcome is 2 squared. So y squared plus the utility in the normal state times that outcome squared plus probability of the high state times that outcome squared. And this is equal to 18.67 approximately. And similarly for B, the probabilities of the different states times the utility of those states, if that's indeed the state that would be realized. Okay, so we see here that doing well in the high state doing well when you have high income, if you wish, gets more weight, which means that this decision maker has a higher expected utility of action B, the one that does best when times are good, if you wish. Just as with risk aversion, we can also illustrate this in a figure. Okay, so we have states on the horizontal axis, and we have utility on the vertical axis. Okay, so we're focusing for simplicity here on just one of them. So let's look at utility of action A here. So if we're in the, let's write the different states here, low, normal, and high. So low is 2 squared, so intercept here will be 4, and then 16, and then 36. So we're going to be having something like this. Okay, so the utility function is increasing, and it's increasing at an increasing rate. Okay, so another word of saying that is that it's strictly convex. You put more weight on the high realizations. Let's look at what happens if we're doing a mean preserving spread. So we're putting more weights in the tails of the distribution here. So instead of probability of 1/3 of each of the states, we say that probability of the normal state is 0. You know, times are never going to be normal. And we're just going to be in one of the extremes. Okay, so either we're going to be in the high states, in the high state with a probability of 1/2, or we're going to be in the low state with a probability of 1/2. Okay, so that's a mean preserving spread in that expectation things are still normal, but you know, we're not going to be there. We're going to be in one of the extremes. So expected utility now 1/2 times expected the utility of being in the low state. So 1/2 times 2 squared plus probability of being in the high states, 1/2 times utility of being in that state, and that is equal to 20. And we should probably clarify that this is the utility of action A after the mean preserving spread, where we're looking at a case where there's more probability distribution in the tail. So in this case, we can say that, well, the utility maker is, or decision maker is going to be either realizing utility of 4 with a probability of 1/2, or utility of 36, 6 squared, with a probability of 1/2. The expected utility, the expectation between those is given by 20. Okay, and that is higher than the value would be if there were no risk. If this decision maker were sure that we'd be getting 4 for sure, there's no risk, what would her value be then? Well, that would be 16, right? 4 squared. So she likes the risk, more probability mass in the tails makes her expected utility higher of this gamble.